Cool. So yeah, thanks for coming again. I am going to talk about Haskell. Don't worry. For those who didn't read the abstract, it's kind of I think one of the things I've really come to love Haskell in recent months is the sort of the code generation features, which I think is is maybe sort of obvious in little places here and there, like deriving EQ and stuff like that. But I think giving a bit of like the sort of the feel story. Like when I first started this job, I'd come from a world of like completely mutable types, like automatic dependency injection using properties in C#, stuff like that. So we set about, like the first few of us coming from this quite difficult to manage world, being very explicit about lots of things, trying to avoid like what we saw as the trap of things like Ruby on Rails, where a lot of things are implicit, like convention over configuration. Actually, I feel like in recent months, I've started to change my view on that a little bit, because if you do these things in Haskell, because you've got things like the type system and a decent amount of soundness around the principles you apply to generate code and get rid of boilerplate using things like convention over configuration style stuff, it actually seems to work a lot better. So, actually I have deep regrets over not embracing things like generics a bit sooner. So that's kind of what I'm going to talk about today. So, what's my first slide? Oh yeah, so I'll quickly talk a bit about the deriving clause in Haskell, specifically GHC Haskell, which is, the standard these days. So I'll start with a little new type. So I've got new type T, which is a new type of an int. I'm sure we're all familiar. Like a new type is it's literally a way of saying to the compiler, these two types are different, but at runtime, it's going to look like the underlying type, right? So it's going to look like an int. And I'm going to say, please derive show for this type. And so the question is, what happens, right? So show is it's a special class, like it's a class that GHC knows how to derive an instance for. So in general, if you write something like this, you might expect T42, right? Because the compiler writes, it doesn't actually look like this, it's smarter, but the compiler writes something like this. It says show TX, you do that by writing T, I forgot the space, classic. And then you show the X, which is an int, and showing an int is just print the number. So you get T42, right? Now, that's great, but as I said, new types, nearly the sole reason you introduce a new type normally is to introduce a new type, but you don't want to do any of the work of talking about the underlying representation all over again. So, a common case here is like, I might want to be able to add two T's together, so I want to make T an instance of num, but I don't want to have to write the instance for num because they're just ints. So please, what I want to say to GHC is just use the instance for num int, but make it work for T's, right? And so GHC has a mechanism for doing this. It's called generalized new type deriving. And you can use that for any class. It basically says if you've got a new type and the type you're wrapping has some type class instance, take that instance and make it work for my new type just by calling the one beneath, right? So if you were to use this for show, what you get is just 42, right? Because GHC says, I'll just use the show instance for X, so you get 42. The problem is, which do you expect? Because if you introduce this pragma, it is actually deterministic. I think you always get the built-in one, not this one. But there are actually two possible good answers for what you should get right, and it's tough to know which one you want. And actually, until recently, it was impossible to say which one you want. You just get the one you're given. Tough. It turns out there's actually a third way to derive stuff as well, which is way more recent, which is, so I'll just slap through an example on this. So, type classes in GHC, obviously you can write your own, good news. You can give default implementations for their methods. So here I've just made up a terrible type class because it has no laws, sorry, which says, a type A is a member of the class 2 of if there's some way of like taking an A and making 2 of it, say. And here's a default implementation which says if A is an instance of the num class, you can implement this method just by writing a function that doubles its input, right? And then I might say, and here's a horrible line, make T a new type of int and derive show, so that's going to be the built-in show instance because show's magic, num using the generalized new type trick, so as in Tx plus Ty equals Tx plus Y, and then I want you to derive this class that I wrote, okay? And there's an extension GHC has called the wonderfully named derive any class, which GHC says, I will derive any class for you by, I will just write an empty instance. So when you write this, GHC writes this. And that works because T is an instance of num, this instance will be picked. So when you write 2 of T42, you get T84. Right, so that's wonderful, right? Because it's probably written about, I mean, in this example, 6 probably lines of code for me, but 6 lines of code that are utterly boring, tedious, blow up the file I don't want to write. But to the casual observer, who knows which method it's using, you know, to derive these classes. So, recently, I think it's probably 8.2 of GHC, maybe it was 8.02. They added yet another language extension, because we haven't got enough, called Deriving Strategies, which lets you state exactly how you want an instance of a type class to be derived. So what I just wrote is equivalent to writing new type T equals T, deriving using the stock mechanism. So there are some special classes like show, EQ, ORD. Derive an instance for show using the stock mechanism, derive an instance for num using the new type mechanism, and using any class, i.e. just write an empty instance, derive my custom 2of class. So it's a bit verbose, but at least you know what you're getting. It's actually super dope, because before this, there were certain things you couldn't do, like you couldn't derive, I'm pretty sure you couldn't derive new type show. I forget the exact combinations, but so now GHC in the latest version has this. It's really handy, and I'm going to spend some time talking about how you can abuse it, because that's what I do when GHC adds a new feature. I'm not the good guy who submits the bug report saying it breaks this one. I'm the guy trying to find out how to break it for personal gain. So I'm a broken record. I talked about this problem several months ago at the Haskell Exchange. I'm going to talk a bit about it today with some new toys. So the problem I have is, as Tom very candidly said, everything we've worked for here is to build a glorified form. Thank you, Tom. So the problem with forms is that they're filled out incrementally, right? Like, you know, you might have a 20-field form, and the user's going to type a bit here, a bit there. Some fields might be invalid until they're done, that sort of thing. And so you're collecting this data, you know, and waiting for it in the back end is some beautiful type somewhere that says a mortgage applicant is this thing, and it's a record, and it's strongly typed, and it's lovely, and it's full. But the reality is you can't talk about that thing until you've got all the data. So in the meantime, if you want to do things like saving as people type, you've got to store this intermediate data, partially collected, probably not valid, that sort of thing. And what do you store it in? So I won't spend so much time talking about all the possible ways to do that. I did that to death at the Haskell Exchange, and they were all wrong, thanks to many questions from the audience. So I'm going to just talk about one of my favorite wrong ways to do it, which is let's just use a map, right, where everything I'm collecting is just, each field has got a key, like the mortgage amount, or like the person's name, or their age, say, and the values in it are just, you know, the types in those fields. Which means that basically I get optional fields everywhere for free, right? Because if something's not in the map, it's like having a big record with maybe in or something like that. The problem is that my fields have different types. Like some of them are, you know, sterling pound values. Some of them are like strings. Well, non-empty strings, strings without special characters in, all these kinds of things. And maps, like so many of the great container types in Haskell, are homogeneous, which means all the values in the map have to be of the same type, right, like a list. So, I went into detail about this at length at the Haskell Exchange, how you solve this particular problem, but, you know, the sort of naive way is you say, fine, we'll just have a sum type that encapsulates all the possible kinds of values we want to capture, and we'll have a map from some key, which is the sum of all the keys, to some value type. That's super ugly. So, you know, you go through 30 slides explaining why it's ugly, and you arrive at the dependent map situation where you say, well, actually what I'll do is I will index my map type by a GADT K, which has an index which tells you what type that key points to. So the name K key is of type key name, so when I look it up, a KA in a DMAP K, I get maybe an A. So that then lets me say, look up name K is of type DMAP K to maybe name, look up age K is of type DMAP K to maybe age. And they're just some new types down there. This, though, is really cool, and actually we use this in some of our code. The problem is it comes with boilerplate, right? So GADT's sick. GADT's not well understood by everyone's favorite compiler. So it's like, you know, boilerplate alert. So you might not be able to see this, it's a bit of a smaller font, but firstly you've got to write some special EQ instance, because EQ doesn't work on GEDTs because if you've got like name K, age K, they're different types. You've got key name and key age, and EQ says take two things of type A, which this doesn't. So, you know, it's fine. The library provides its own class called GEQ, and off you go writing an instance for it. So that's like 3 lines. Oh, but wait, I've actually got 200 keys, so off you go. Don't worry, I'll rip out the template Haskell, and then, which we do because it's slightly less than, you know, even if you're using Dvorak, like some of the crazy buggers on the team. Then, and also you want to serialize it, so you have to say for every key, like, you know, what's a nice string representation of it. And again, like, you know, you can reach the template Haskell because you can't derive generics for GHCs, or, you know, or you write the function yourself. It's just, it's literally the worst thing in the world. Asterisk. So.
You can write a normal algebraic data type that kind of mirrors your GADT without the type indexes, and then you can convert back and forth with a little.
You can. So the point the gentleman in the front is making is that you could write an ordinary type for your indices and convert back and forth and use the generic code, but you've got to write the code that converts back and forth, haven't you?
There's a tool that does this automatically. There's a paper about this called Ghostbuster or something like that.
But that tool is, I mean, is akin to using template Haskell, right?
Yes.
Which is okay. It's fine. We've all done it. But
it helps you in a way.
Everything helps you in a way with template Haskell, doesn't it? Here's that function you're looking for. Trick. So, yes, there are ways around it, and as I say, we do employ this in our code base today to a degree, and we just suck it up. But it hurts. So, it came to me in a dream. So, you know, the keys, they're very say what you see, aren't they? Like, every type in this map is going to have a key, like name K, age K. Why don't we just use the types themselves as keys, right? Which you can do thanks to another feature I've been loving, which is type applications. So, you end up with the most dangerous looking type ever, tmap, no indexes. And you say to look up in a tmap, it's just, I always forget that that's how projectors work. It's tmap to maybe A, but with a visible type application. So if you haven't seen this, so this type is ambiguous, right? If you called lookup with a tmap, GHC would say, what's A? And until recently, there was no way to say to GHC, A is this. But now you can by specifying at name, which will fill in a type argument, basically, so we call this type application. So you can say lookup at name, and that will magically give you a function of tmap maybe to name and tmap to maybe age, which is awesome, because now I don't have to write the keys, because the keys already exist. They are the types. But, I hear you say, some types appear more than once. No, they don't. You just need more types. So like, you do mortgages, you do joint applications, there's going to be 2 names in that map. Well, no. There's a primary name and there's a secondary name. They are different things. So we should say as such. And yes, if you're thinking, well, you just end up creating loads of new types, that is true, but it's also okay because they are part of our domain model. But if you hate domain models, and it happens to us all at some point, you could just use tagged and type level strings. Ask me about that afterwards when we've both had some substance. So you can do that and the types work out as you expect. It's great. No more keys. But you can't do serialization anymore, right? Because now you want your secondary age to be serialized beautifully, but it's this, you know, secondary age and you've got names. How do you get the strings back? That's okay. We just need to use type level strings and associate with each type A some S, which is a symbol, which is what GHC's type level strings are called, such that A determines S. So for instance, I might say the type name is, I'll call it a field, and its key will be name at the type level, right? And then I'll define a function, field key, which basically lets me take the type level thing and reflect it down to the value level. So I can say the field key for at name, and it will give me the string name. Okay, so that's all right. Obviously, this is some boilerplate now, right? This is an instance I have to write. And how do we do the secondary thing? Well, you know, where there's a will, no pun intended, there's a way. So I've massively, this isn't actually what you write because you can't apply type families and things like that in a class, but the feeling is you can say, don't worry, we'll introduce another class group, which takes things of kind type to type and associates a symbol with them. So you can say, well, secondary, which is takes a type and gives you a secondary A, will prefix secondary onto something. So if you say field key secondary age, you get the magic secondary age, right?
You could derive all this from genetics.
What was Tom's thing? Next slide. So now, and you might be wondering, why did he put the symbol first? That's stupid. It is stupid, but it's craftily stupid, which is GHC's favorite kind. So now I can say, hey, here's an age. Derive show in stock, just so I can use GHCI. Derive JSON using new type, so I can serialize to and from JSON. It looks like 42, not age 42. And any class derive me field age, because the default because the class is empty actually, there's no need for it. And then I can just write. So now I have a nice file where I describe my domain model in sort of the terms I want to talk about, which is here's the type, you know, a primary, maybe some nice haddock, not here, but you know, conceptually that's what everyone does, right? And it's great. It just works. So all that in mind, it feels like we've got enough tools to write the library, right? And the library is actually not too bad to write. So, you know, you just say, for instance, I've arbitrarily picked JSON as my serialization mechanism here, but you could use dynamic here and figure out some other tricks to do it. But under the hood, you just say, well, a T-map maps from these string keys to JSON values. That should be value, sorry, if you're using ASIN. And then insert and lookup are kind of the obvious things. So you say, well, inserting an X into Tmap, and this is kind of the weird thing. You don't need a key here, you just say insert this A, and as long as A is a field, I can determine the key will be the value level reflection of S. So I say insert, generate the key field at S as the string key, use that to insert X into M, job done. And lookup, I've been very naughty, I've forgotten two things. You need two JSON X here, and you need fmap from JSON here. But ignoring the in and out of JSON bit, this is how it works. Lookup, you just say, well, generate again the key field, tell me what the value level string representation of S is, and look that up in M, and out comes the value, right? So, oh yeah, there's a bonus point of this slide, which is, even here I can get rid of some boring code. Like, what does the empty map look like? Oh God, you know, let's write empty equals tmap m.empty. No, screw that, let's just derive semigroup and monoid. Using new type mechanisms. And that works in 8.2 now because semigroup is in the right place. So that was a nice little bonus. Right, so great. You've written a domain model for a form that's completely partial and got all this nice trickery so that you can serialize these incremental updates to the database using JSON blobs, all that kind of stuff. Now you're ready to turn it into a real thing, right? So you're like, great, request comes into the back end, load up this map. Yeah, it's got everything I need. I want to turn it into the actual domain type that I want to send through the rest of the code base, right? This isn't, you know, this isn't forever. I don't want to be sending these maps through the code base and everyone has to check every time. Is there a name there? Is there an age there? I want to, as soon as possible, get rid of that filth that I just evangelized and get into normal Haskell types because that's where the money is, right? So let's say I've got my person type, they've got a name, they've got an age. You know, now you want to write this function that says, take a Tmap, give me maybe person. Well, because we went to the trouble of making that map effectively a type indexed product, that is, everything in it is uniquely determined by its type, that code is boilerplate, right? It's completely mechanical. To the point where you can derive it. So if person is generic, so this is GHC support for generics, which basically means any type that isn't a GAD, you know, asterisk terms and conditions apply, any type can be represented as a sum of products. That is, you know, one or more branches of constructors which each has a group of types in it. So here, for instance, you can, you know, person can be represented, it's basically isomorphic to pair of name and age. And so all you have to do is write G from Tmap, and what that effectively you want to turn that into is, well, do a lookup of age, do a lookup of name, they both return maybes, and fmap person over those two things. If they both come back as just, you'll get just a person, otherwise you'll get nothing. And yeah, the way you do this is generics. GHC's generics mechanism, again, this is like, what's the word? This is sugar. This isn't, it's a bit more detailed than this. It's substantially more detailed than this, but the general feel of it is it says for any type that's generic, there's a type family rep that says this is roughly what it looks like. So this star is product, so it says a person basically is a product. Well, sorry, a person is a type that has a constructor called person, so this is a type level string, right? And that constructor is a product of two selectors, i.e. named fields. One is called pname and it has a name in it, one is called page and has an age in it. And so you can write type class instances basically that walk these things. So you end up saying like, You know, if S1 has type name, you could do a lookup of that type. If some representation L and R are both lookupable, as it were, then the product of them is lookupable by using this jiggery here. And that's great. So, you know, the library writer, me, writes this code once, like some generic hackery, and then anyone who uses my map type can just pull stuff out of it like this without caring. I mean, if you wanted to go even further, I haven't, because even I have my limits for talks. You could make a type class that says, this is the class of types that can be built from maps. And the default implementation for that is just to use this. And then you could write, oh my God, why didn't I put this in the talk? You could write data person, deriving stock generic, deriving any class from map, and it would write this code for you. Great idea. The next version of this talk will totally have that in. So yeah, generics, the rest of this talk is going to kind of devolve into what you can do with generics. But the key realization I want to stress is that what you can do with generics when you make your products index by types sort of is a larger set of things, because type uniqueness gives you a lot of nice assumptions that you can exploit, such as, so now you have the classic problem, which is, I think they call it inheritance in object-oriented programming, which is people don't always look the same, right? So, you know, at stage 1 in the application, you might only know someone's name and age, but later on, you might care about how much savings they have to see if they've got enough to buy a house, say. And these are kind of two different types of person. So like the quick hack, you know, we've all been there, is just to say they have a savings field, it's maybe savings. So it could be nothing, or it could be just some savings. You know, the reality is you have two different types, right? Sometimes you have a person with no savings, sometimes you have a person with savings. And you know, you start playing the usual tricks, you know, we're all familiar with this one, where you just, you know, say parameterize it by the things that can change and hope that there's a functor, it was a functor, isn't there, that can save you. But the reality is there are multiple types of people, and you are trying to avoid writing all those types every time. Why are you trying to avoid writing the types? Well, at least when I try to avoid it, it's not because writing the types is annoying, because like the types, again, they're part of your domain model. At some level you have to accept that and embrace it. What's annoying is writing all the functions between those types, right? So, you know, you say, fine, I'll just acknowledge that a person with savings is like a customer, or a qualified customer. But now I have to write a function that says, well, if you've got a person and some savings amount, you can make the full customer, right? But, again, if all your things are type indexed, you don't have to do it. Just derive generic, and you can write a function, say gexpand. This slide doesn't do us justice. There's like 400 lines of crap behind this, but you know, so now you've got the two representations. You say a customer looks like this. Customer looks like this, which is the same as a person, but it's just got this extra savings thing. So you have some type class code that walks these two lists of types and says, oh, okay, this one's just missing the savings. So what I'll do is I'll generate a function that takes a person as its first argument, uses record wildcards. I'm not endorsing record wildcards. It's just the only way to fit it in this slide. I love record wildcards. So this says take a person. This, if you don't know it, this is called record wildcards. It basically says take the construct as a person and implicitly pattern match them into scope. So this says I'll generate a function that takes the person and works out what the missing fields are and just tacks them on to the end. So you can generically generate something that takes a person and then effectively the diff as a set of arguments and just magically works. So now, and again, you could probably stick this in a type class. Yeah, that smells good. And you're back to where you want to be, which is let's just write the types, because isn't it all about the types? And yeah, it's horrific, but again, all this lives in the library. Like, no one has to know how gexpand works, right? And I guess the craziest thing of all is that GHC is got a bit of a fetish, right? GHC's fetish is type classes. Like, GHC loves type classes. Like, it's designed to optimize them, because the way type classes are implemented, if you do it naively, like pure script, then you end up passing extra arguments to every function. So, you know, the guys in GHC HQ spend a long time optimizing away these arguments, inlining the crap out of them. And so what that means is actually, because generics are implemented as type classes, a sort of nice side effect you get is that sometimes, not always, but sometimes, the core, like the code that gets generated for gexpand literally looks like this, because GHC will ruthlessly inline it until it's done, and you end up with this. It does mean it takes 4 days to compile, but the resulting code doesn't take 4 days to run. Swings and roundabouts.
We should have a flag to produce a type error if GHC cannot optimize away a dictionary.
The point was, we should have a flag that means we know whether or not GHC is optimized. There's actually a library called GHC Proofs, I believe, which is pretty cool. It lets you write a unit test where you say, here's the handwritten code, here's the gexpand, and the test will pass. It will basically uses the GHC's API to run both things through GHC's codegen, and if they're the same, it passes, and if they're not, it's fails. So there's a library called Generic Lens, for instance, that uses generics to generate lenses, and they have a set of tests in their suite that says, do these optimize down to the lenses you would have written by hand? Like anyone's writing lenses by hand, but you know what I mean. And they all pass currently, which is ridiculous because that code is horrific. But GHC just chews it up. So I think that's my last slide. It is my last slide. So yeah, I guess the take-home points are, like, yeah, labeling your fields is great, but like precision in types, it's just, the more I work with it, at least the harder it feels to trade that away. Like the more precise you are in types, the more you can get the compiler to do for you. And I guess that's kind of the theme some things are taking. Like if you look at the progression of things like dependent types, it's about writing the types and having the compiler derive your program, right? And this, don't get me wrong, there's lots of pitfalls with like full-blown dependent types, but this feels like a really nice sweet spot where you can say to GHC, do you know what, I'm willing to go a bit more crazy than I would normally on new types and pay some of the syntactic costs of wrapping and unwrapping here and there and thinking about really what it means to be a name and stuff like that. But on the plus side, I'm never going to write a JSON instance, I'm never going to write serialization code again. Like, you know, and these ideas aren't new to the Haskell community. We have lots of template Haskell, we have lots of generic stuff, but like pushing it to its absolute limit and like asking, what does the best developer experience look like? Which is kind of what started all this. Like, you know, the stuff at the start, like the GADTs, it's all well and good. When you've got 200 keys, like, you know, and someone joins your team, and you're like, oh, I just want to add a field to this form. You're like, come here. And you open like, I don't know what it's called these days, like hell.hs, and you're like, Monday, all this will be yours. Like, it'd be much nicer if you could say, here's a file of types. You know what types look like. You know that you can derive stuff for types. If you want to add a field, just make a new type deriving field. And you'll get a type error if it doesn't work, rather than 50 type errors 4 pages long. So, yeah, I think I've rambled enough. If I'll take some questions.
So I think that this trick of type uniqueness could work quite nicely for defining data frames, so libraries for working with big data like pandas, because in Haskell those libraries usually tend to use extensible records, and when you have to compute what's the type of doing a join between two different data sets at the type level, then things get quite hairy. Whereas here you've removed all that. Have you looked into something like that? So your map is actually just a line, just a row. And then what happens when you have many rows?
It isn't. So I guess the question, if I may rephrase it, is roughly, how does this compare to extensible records? What are the trade-offs? What are the downsides kind of thing? Like, so an extensible record is, you know, you have an ability to say, I've got a pair, A and B, and later I want to add a C to it, but I want to, it's sort of like an H list, say. This approach, you could sort of say, I've got a map, and I don't need to know up front what types are going to go into it. So it's kind of got a similar vibe, because you could insert an int, later you could insert a string, and it's all fine as long as the types are unique. One difference between this approach and that is that, as I sort of highlighted, is that you can't statically tell what is in a map. You know, it can accept any type that's JSON, but you can't statically tell what's in it. And actually, the last talk I gave was kind of looking at the opposite approach, which is I really wish I could know what was in that map statically. And so I looked at, you know, indexing it by a list of pairs of symbols and types, or in the end, I wrote a GHC plugin that lifted map to the type level, because when you've got a list of pairs and types 200 lines long, GHC literally takes a day to type check it. So that's in the end, I basically gave up and said, do you know what, like getting you to track statically what's in this map is too expensive. So the trade-off here is it's really cheap now to put stuff in, but at no point statically can I enumerate everything that's in it, which is why you end up with the compromise of saying the values are just JSON. You have to pre-serialize and post-deserialize.
Yes, I think one potential pitfall could be that when you're working with big data, you have to change the way you store it. So instead of storing JSON blocks, you want to store arrays.
Yeah.
So it's sets of arrays. And in GHC, in order to store arrays efficiently, you have to use unboxed
Yeah, or U vector or something like that.
And in order to be able to use a box array, you need to know that the type of that field is a limited type.
This feels a little bit off topic, but this feels exactly what data parallel Haskell was created to solve, which is yet another project that was consigned to the annals of, actually, let's never bother doing that properly. So data parallel Haskell says use data families to do that. So data families are, they're like type, that's bad. Circular reasoning is good because it's not bad. A data family is where you can, you know, with a type class, you can say, for each instance of the class, you can say, what do the methods actually look like? A data family is like that, but you can say, for each instance of the class, here's what the data constructors look like. So you can say, like, data family array A, and you can say, data family array int equals unboxed array of ints. And what data parallel Haskell let you do was say, data instance array pair AB equals pair array A, array B, so you get like the nice array of structures flattening, that kind of thing. So data families are quite powerful for letting you instantiate things at different types. It's not quite an extensible records thing though. They are open, so you can at any point say, hey, here's a new way to instantiate this data type at this type. Yeah, but it's statically open again, it's not runtime open. But that might be another thing to look at.
Any problems sharing types from the back end to the front end when you're using this generic electrically?
The question is, do you have problems sharing types between back end and front end? So, I guess what you mean by that is, if you use generic to generate your JSON instances, for instance, do you get silent breakage when you change your type definition and suddenly your serializer's changed? Currently, we don't share types between the front and the back end, so we don't get that. We do use generic instances for JSON serialization, which some people are vehemently against for this exact problem, which sometimes breaks our database because we have an event store, so we use JSON blobs in the DB. And so if you silently change something, it all works fine, and then you push to prod, and the 4 million events that are sitting there already don't deserialize anymore. I don't really know what the trade-off is there. I know I hate writing JSON deserializers, so the way we currently tackle it is with an ever-growing suite of integration tests, which I believe have value beyond that, but also help save this case. I don't know where I'm going to end up. I do like not writing the JSON instances, but equally I feel like you might end up at a sweet spot where you just say, look, on the boundaries, where I'm talking to the database or like at the hosting layer, the HTTP layer, I manually write JSON instances because it's valuable and those are smaller, but intra-code base, as it were, between domain layers, I'll take the risk and use generic deriving because the types are shared. Sharing between two disconnected bits which both have generics, you might get away with that. So PureScript has generics as well and can derive generic JSON. You just have to make sure that the generic libraries agree on how they derive their JSON, but if you use a piece of code that generates your PureScript types from your Haskell, you do get away with it then. The problem is always users, right? And in this case, I mean third parties. So like, you know, we have an API that obviously we used to serve our own web page, but as we onboard people who want to use our API to source mortgage data for their product, that's when things get really dangerous with derived code. Because, you know, I change a line, all my code updates, and then I don't get a phone call, but you get like a Slack message or an email saying, hey, everything just broke. You're like, shit. So, yeah, fine line. I do hate writing that code though, but evils we live with.
So, when you compare the dependent map and the type map, one advantage, I think, of the dependent map is that you use a type for the keys. So in a given context, you can tell when you're asking for a key that makes no sense, and the compiler will reject that.
Yeah.
And that I don't think it will happen with the type map.
No, so the point being made is that with many of the other solutions, including the one I presented at the start, where you have, say, a GDT describing your keys, it's possible for the compiler to tell you when a key doesn't make sense. So for instance, with my thing, you could literally say insert maybe IO unit, as long as it had instances of the class. I mean, if someone defines that, they're so fired. But it would work. And the point being made was that the nice thing about the GDT is that you can't just make up a constructor of a GDT. So if you type like insert, you know, third applicant name, GHC will be like, that key doesn't exist. Or some of the other solutions I discussed, you can use custom type errors to say, hey, these are the keys that are actually available. But again, here, there's no closed set of keys. There's no way to enumerate type class instances without using template Haskell. And even that's not reliable because type classes are open. So yeah, the big compromise, which kind of ties into your thing again, is that here the compromise I've made is I kind of enumerate the possible set of keys, but I get cheap enumeration of the values. And the previous thing I was trying was I could enumerate all the keys statically, but it made enumerating the values incredibly expensive because you end up traversing the whole set of keys to work out which JSON instance to pick. It's really... the next talk is probably going to be just use Idris, but then your code performs like Idris, so which is to say not as fast.
Maybe you can overcome it, like parameterizing the map with a constraint or something?
Maybe I can overcome it by parameterizing the map with a constraint.
And then you have an extensible record.
To a degree. I guess that's what I've done though. By making the type JSON, I've effectively implicitly parameterized it by the constraints to and from JSON, which is reflected in the insert and lookup, which is, yeah, exactly. You end up basically saying, you either do that, or what you're suggesting, which is you just, every value in the map is actually a pair of the value and its dictionary. And so you end up paying a cost there. But it's just different solutions to the same problem. There's a massive space here and I'm still not sure what's the best, but this is currently the most interesting for its abuse of generics, bloody motion sensors.
I'm wondering whether the lights are trying to give us a...
Oh yeah. Someone's out there with a fuse box, just like... yeah, if there's no more questions,
Final question?
or I can walk myself off.
I think let's thank
Cool.